Hello everybody, my name is Iman at SID. Welcome back to my YouTube channel. Today we're going to go ahead and cover chapter 12. Now, in chapter 12, we're going to be talking about the structure and properties of alcohols and phenols, really focusing on the acidity of alcohols and phenols. Then we're going to talk about preparation methods as well as reactions of both alcohols and phenols, and hopefully do a couple of synthesis problems at the end to put it all together. But first, an introduction to alcohols. What is an alcohol, you might ask? Well, an alcohol or alcohols are compounds that possess a hydroxyl group, so an OH group, connected to a sp3 hybridized carbon atom. And these are characterized by name with the ending OL. Now, alcohols are more acidic than amines or alkanes, but they're less acidic than hydrogen halides. And if you remember, we determine acidity by evaluating the conjugate base. So if we take all of these functional groups here, alkane, amine group, alcohol, and alkyl halides, if we take these groups and we deprotonate these molecules to obtain their conjugate bases, the most stable molecules, the molecules that can stable that negative charge better after deprotonation, when they are protonated back again, make four stronger acids. If you guys remember, we covered this in chapter 3. All right, so the most stable molecules in their conjugate base form have the highest acidity, which is why our alkyl halides are the most acidic, followed by our alcohol groups, then amines, then alkanes. All right, so alkyl halides most acidic, and then going down is less acidic. All right. Now, another question you might have that's important is, well, how do we deprotonate an alcohol? Well, a strong base will do the job. Something like sodium hydride would work perfectly to deprotonate an alcohol. Something else that would also work is using a metal like lithium, sodium, potassium. These metals react with the alcohol to liberate hydrogen gas, producing the alkoxide ion, which is the conjugate base of an alcohol. All right. Now, there are several factors that affect the acidity of alcohols when we're relatively comparing. One thing is resonance. The presence of resonance can lower the overall pH of the alcohol, making it more acidic. And again, this essentially goes back to our ARIO rules, if you remember. Okay, if you have an alcohol, all right, if you have something like this, all right, this is an alcohol, versus if you have something that looks like this, but there's some resonance here, all right, which one would be more acidic? All right, the one with resonance. All right, induction also plays a very important role. The presence of electron withdrawing groups can increase acidity. Again, this is a nice reminder of our area rules, and we can do something very quickly here to demonstrate this. So something like this, just a normal alcohol versus, oh, let me fix that up, versus something like this, Cl, 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 right? If you compare just your normal alcohol versus your alcohol that has these electron withdrawing groups nearby, this is going to be more acidic because of those electron withdrawing groups and the inductive effect they play. All right, solvation, not solution. I wrote this wrong. Solvation, all right, also plays a role in acidity. Molecules that are easily solvated, so molecules that are not sterically hindered, display greater acidity, relatively speaking. So if we're comparing something like ethanol versus something like a tert-butyl group like this, all right, ethanol is more easily solvated because it's not sterically hindering like the tert-butyl group, therefore more acidic. All right, so it's something to keep in mind. 3 rules that have an effect that factor into acidity are resonance, induction, and solvation effects. Now, with this nice profile we've built up on alcohols, we know how to identify them. We know their acidity, pKa between 14 to 16. Usually we know how to deprotonate an alcohol. And we also talked about factors that affect the acidity of alcohols. So we have this complete profile on alcohols. Let's jump into all the methods and techniques we can use to prepare alcohols. So for substitution, we can use either SN2 or SN1 to prepare alcohol. So for substitutions, alcohols can be prepared by substitution reactions in which a leaving group is going to be replaced by a hydroxyl group. Now, a primary substrate will proceed through SN2 reaction. So use a strong nucleophile like sodium hydroxide with a primary alkyl halide. Through SN2, we're going to replace this chlorine with a alcohol group. And there you go. We've prepared an alcohol. All right. Now, if you have a tertiary substrate, this is going to require SN1 conditions. So you want to use a weak nucleophile like water, right? This is all going back to our substitution reactions from chapter 7. Just a friendly reminder here. All right. So tertiary with a weak nucleophile like water, this will proceed through SN1. We're going to replace that chlorine with a hydroxyl group. And again, we've prepared an alcohol. Now, something to remember with a secondary substrate, neither SN2 or SN1 is particularly effective for preparing a secondary alcohol. Under SN1 conditions, the reaction is going to be a little too slow. With SN2 conditions, we're actually going to favor elimination over substitution. So preparing secondary substrates, preparing secondary alcohols using substitution reactions is not the best way to go. Now for addition, if you remember in chapter 8, we covered 3 ways to add a hydrogen and an alcohol group to both sides of a double bond. These 3 techniques were acid-catalyzed hydration, oxymercuration, demercuration, and hydroboration oxidation. Now, if you remember, for acid-catalyzed hydration, you're using something like dilute sulfuric acid, and it's going to proceed through Markovnikov addition. That means the hydroxyl group, the OH group, the alcohol group, is installed at the more substituted position, hydrogen less substituted position. It's a useful method if your substrate is not susceptible to carbocation rearrangement. That is usually the caveat with acid-catalyzed hydration. You have to be aware that sometimes carbocation rearrangement is possible, which usually means a mixture of products in the end, which might not be good if you're trying to prepare a particular product through a synthesis pathway. All right, so keep that in mind. Now, oxymercuration, demercuration, also, this is the reagents for this. You are doing this through Mark addition. Now, this also has to be, this is also through Mark addition. It does not involve carbocation rearrangement, which is good. So if you don't want a mixture of products, you just want your Mark addition product through hydration, then this would be a good pathway to take advantage of. Now, hydroboration oxidation, while still adding an alcohol group and a hydrogen to a double bond, it occurs through anti-Mark addition of water. So your alcohol group will go to your least substituted position, all right, while your hydrogen to the more substituted position. So these are all important things to keep in mind in regards to preparing alcohols using addition reaction. All right, with that being said, let's do a few practice problems really quickly. Identify the reagents you would use to accomplish each of these following transformations. This is going to be one-step synthesis kind of problems. All right, so if we look at A, we're replacing that bromine with alcohol. This is pretty much the only thing that's changing. Now, an important thing to note is that this is tertiary, a tertiary substrate. So what's going to be happening is we can replace the bromine to this alcohol group but it's going to occur through SN1, so we want a weak nucleophile. So the reagent we would need to accomplish this is simply water. Water will convert that bromine to an alcohol group. Now, if we look at B, all right, again, we're converting this halogen to an alcohol group. Our substrate is primary, so we're going to be doing this substitution through SN2. That means we can use a strong nucleophile like sodium hydroxide. All right, now if we look at C, all right, what we're doing is we're starting off with this double bond, and what we're going to be adding is an alcohol group to the more substituted position, hydrogen to the least substituted position. You can do this either through acid catalyzed hydration or oxymercuration demercuration, because you're not going to have to worry about carbocation rearrangement. So either one of those pathways would work. We'll just do something easy, acid catalyzed hydration, since we don't need to worry about carbocation rearrangement here, because you're going to form your more stable carbocation anyways to begin with, so no need for rearrangement. All right, so you can do acid catalyzed with dilute H2SO4, or you could do oxymerc demerc if that is what you would like. Fantastic. Let's continue now that we've done these practice problems with more alcohol preparation techniques. Another alcohol preparation technique is through reduction. Here we can start with something like a ketone or an aldehyde, where there is a double bond, right? That carbonyl, carbon double bonded to oxygen. And what we can do is reduce it to a single bond where there is now a alcohol group instead. So the conversion of a ketone or aldehyde to an alcohol is a reduction reaction. So that means it requires a reducing agent. We're going to cover 3 reducing agents now. These are going to reappear a lot in OChem 2, so make sure you at least remember one to use for all your synthesis that you will be doing in OChem 2. All right, so with a starting ketone or aldehyde, you can use hydrogenation in the presence of a metal catalyst, such as platinum, palladium, or nickel, to reduce this double bond to an alcohol group where there's also a hydrogen installed. All right, so this can be used as a reducing agent. This only works under certain conditions, so it's actually not as commonly used. Something else that can be used as a reducing agent is sodium borohydride. Sodium borohydride is a common reducing agent that can be used on ketones or aldehydes. It functions as a source of hydride. All right, it functions as a source of hydride, and the solvent functions as a source of hydrogen. Now, in the mechanism, what happens, and we're going to zoom in here, in the mechanism, what happens in your first step is sodium borohydride is going to deliver hydride to the carbonyl group. All right, so sodium borohydride delivers a hydride to the carbonyl group. This is followed by a proton transfer where the resulting alkoxide ion is protonated to form your alcohol. For unsymmetrical ketones, all right, if you had an unsymmetrical ketone like something like this, okay, you're going to get a mixture of stereoisomers as product. So you'll get a mixture of stereoisomers as product. So if this is your starting ketone and you're reducing it through sodium borohydride, you're going to get a mixture of stereoisomers as product. So keep that in mind. All right, now, last but not least, my favorite, lithium aluminum hydride is another common reducing agent. It has a structure very similar to sodium borohydride. It also is also a delivery agent of hydride, but it's a much stronger reagent. Note, it reacts violently with water, and therefore a proteic solvent cannot be present with lithium aluminum hydride in the reaction flask. Now, for the ketone aldehyde, when treated with lithium aluminum hydride, follows kind of a similar mechanism. In the first step, your lithium aluminum hydride delivers hydride to the carbonyl. And then as a final step, you do a proton transfer where the resulting alkoxide ion is protonated to form that alcohol. All right, this is the simplified mechanism, by the way. Again, with an unsymmetrical ketone, you are going to get a mixture of products. A pair of stereoisomers is going to be obtained, right? Because the hydride nucleophile is going to be able to attack here on either face of the carbonyl group. All right, so keep that in mind. Let's jump into some quick practice problems now where we can display what we just learned. Okay, so here's our starting aldehyde. Okay, we're treating it with lithium aluminum hydride. This is a reducing agent. What that means is that this carbonyl is no longer going to be a carbonyl. It's going to be an alcohol group. And of course, there's going to be the addition of an extra hydrogen to make sure your carbon is satisfying its octet rule. All right, so what our product is going to look like then, all right, we keep the same structure, but now there's an alcohol here and of course an additional hydrogen. This is your final product for A. Now for C here, all right, we're treating with sodium borohydride, again a reducing reagent. What's going to happen here, all right, and this is a ketone and it's unsymmetrical. What's going to happen here is we're going to replace this with an alcohol group. Of course, there'll be also an hydrogen attached here. Now, it's an unsymmetrical ketone, which means your products that you're going to obtain are going to be a pair of stereoisomers. So we're going to draw out the structure of this as is. All right, looks something like this. And there's going to be an added alcohol group here. So it can be added to the front face of this to produce this stereoisomer, or your sodium borohydride can attack from the back to get this stereoisomer. All right, so your alcohol will be on a wedge and a dash, and this is the pair of stereoisomers you're going to obtain from this reaction. Fantastic. One more preparation method. Lastly, another way you can prepare alcohols is through Grignard reagents. Now, Grignard reagent is formed by the reaction between an alkyl halide, all right, and magnesium. What's going to happen is your magnesium is going to insert itself between the alkyl group and the halogen. This is a Grignard reagent, all right? It's characterized by the presence of a carbon-magnesium bond. Carbon is more electronegative than magnesium, so the carbon is going to withdraw electron density from magnesium via induction, which gives it a partial negative charge and the magnesium a partial positive charge. All right. In fact, the difference in electronegativity between carbon and magnesium is going to be so large that you can treat this bond as an ionic bond. Now, carbon reagents are carbon nucleophiles, and they're going to be capable of attacking a wide range of electrophiles, including the carbonyl group of ketones or aldehydes. So let's take a look at this mechanism. If you're starting with a ketone or an aldehyde, you can react this with a Grignard reagent, all right, to obtain an alcohol product. All right, so how this is going to happen is your Grignard reagent is going to act as a nucleophile. It'll attack your carbonyl and attach itself there. So whatever your R group is in your Grignard reagent will attach itself to your ketone or aldehyde in this reaction. So if that R group is an ethyl group, you're going to be adding an ethyl group. If it's a phenol group, you're going to be adding a phenol group, so on and so forth. Okay, so it attacks, nucleophilic attack. Then you get a product like this where your oxygen has a negative charge. You've added an R group. All right, now we get a proton transfer. This alkoxide ion is then protonated to form an alcohol. And this is how you can prepare an alcohol through using Grignard reagents. Now, do not mix with water. Okay, this water comes in only after your Grignard reagents, because if it's just reacting with water, it's going to deprotonate the water. All right, so just keep that in mind. All right, so let's do a couple of practice problems to make sure we understand how to do this. Show how you would use a Grignard reaction to prepare each compound below. So our ultimate goal is to prepare this alcohol. All right, how do we do this using Grignard reagent? Well, what we can do is we can take this and use it as a motivation. Use it as motivation as our starting ketone or aldehyde. So I'm going to draw the same structure here, all right, with an alcohol group, all right, and a carbonyl. I'm getting too ahead of myself. All right, with a carbonyl, where over here I'm going to put a hydrogen. So we're starting off with an aldehyde. Why? We're going to play this methyl into it. We're going to put this methyl into this molecule. We're going to add it using our Grignard reagent. Remember, our Grignard reagent has this magnesium halogen group. We're just going to use bromine all the time just to stay consistent, plus an R group. This R group can be anything that we want to add to this starting substrate. We want to add to it a methyl group so that we ultimately get this molecule here. Fantastic. And then, of course, the water comes in as a second step. What's going to happen here then, using this Grignard reagent and this starting material, okay, what's going to happen is, one, we're going to add a methyl group here, which is going to give us this carbon skeleton that we want, all right? And we're going to, instead of this carbonyl, we're going to have an alcohol group, all right? This is the two things that are happening here. We add a methyl group, all right, and we get an alcohol. So the end product of this is now we have this methyl group. All right, our hydrogen is still there. We can draw this if you want to see what it looks like. And then our alcohol group here. And look at that. We started with this aldehyde, and through Grignard reagents, we got the final product that we want. Fantastic. Let's do B. Okay, again, this is the final product we want. All right, we're going to use this as motivation, as inspiration on what we want to start off with. So we're going to keep the same structure as before, and we're going to, right there where the alcohol is, we're going to have a carbonyl. So we're starting with this ketone. Something to notice is we want to add a methyl to this position here. So the Grignard reagent we're going to use is going to be methyl, because that's the group we want to attach. All right, with our magnesium bromide, this is our Grignard reagent. And then water as a second step to get the alcohol. What's going to happen here is we're going to add a methyl here. And then through these other set of reagents, we're going to convert this to an alcohol. And what that's going to give us as a final product is an alcohol here, right? Because our Grignard reagent is going to convert that carbonyl to an alcohol. But we also need to add whatever R group is there. So that's going to be that methyl group. And look at that. We get the product that we wanted. I'm going to let you try to figure out C and let me know what you get as an answer. But with that, we have covered all the ways that we can prepare alcohols. Now what we want to talk about are protection groups. If there is an alcohol present in your molecule to begin with that you don't want to operate on, but you want to operate on a different part of the same molecule, what you can do without affecting the alcohol is you can temporarily replace that alcohol group with a protecting group, react whatever other parts of this molecule you wanted to, and then convert back to alcohol. So let's look at here. We have this molecule. It has an alcohol group and it has a bromine group. We don't want anything to happen to the alcohol group. We just want to work with this bromine to do a Grignard reagent, a Grignard reaction. What we can do is protect this alcohol group, so convert it to something else. All right, proceed through Grignard reaction to operate on this bromine to get an alcohol group there. Then what we can do is remove that protecting group and put back our alcohol. If we never protect the alcohol, whenever we're doing the Grignard reaction, it will do something to the alcohol we don't want. So a good protecting group is going to be OTMS, which is our trimethylsilyl ether. All right, it looks like this. All right, but it's commonly written on a molecule as OTMS. All right, so the reagents you will need to replace the alcohol group to OTMS are this set of reagents: TMS, chlorine, all right, and then ET3N as your solvent. So this set of reagents will convert your alcohol to an OTMS group. All right, then you can go ahead with your Grignard reaction to convert that bromine to a alcohol group with two R groups attached. Then you can remove your OTMS. You can remove your protecting groups using TBAF and replace it with that alcohol group. All right, fantastic. So this is how you want to approach these kinds of problems. If you're only operating on part of the molecule, if there's another functional group that might react in the process that you do not want to change, then you need to protect it. To protect it, you can replace it with another group. For alcohols, you can replace them with OTMS. Go about your reaction and then replace that protecting group back to your alcohol. Fantastic. Now, for preparation methods of phenols, there's really only one we want to talk about. This is how phenols are industrially prepared. You start with a benzene, you convert it to a cumin, all right? And then eventually this gets converted to a phenol group. And this is how phenol groups are industrially prepared. All right, now we want to do a few quick practice problems. Identify the reagents that you would use to achieve each of the following reactions or the following transformations. All right, we're going to look at A. All right, we want to convert this bromine to an alcohol group with two methyl groups. All right, but we don't want to touch this alcohol at all. So our first step is to protect that alcohol. All right, so that's exactly what we're going to do. We're going to protect this alcohol, all right, by converting it to OTMS. How do we do this? Easy. TMS, chlorine with ET3N. All right, what this will do is it'll convert that alcohol group to OTMS. All right, and here's our bromine. Now, we want to convert this bromine to an alcohol group with two methyl groups, okay? So what we're going to do is we're going to first treat it with magnesium. All right, that magnesium is going to insert itself in between right here. All right, and then what we want to treat it with, all right, so when that happens, when we treat it with magnesium, what this is going to look like, I'm going to show you really quickly, is MgBr. And so this now is our Grignard reagent, okay? That means this is our magnesium bromine, and the rest of this molecule is our R group. Okay, so let's think about it like that. This is our R group. So if we want at the end of this to take a carbonyl, convert it to an alcohol, but still have those two methyl groups we want, then to this carbonyl we need to have two methyl groups. Okay, fantastic. So this is the ketone that will react with this Grignard reagent, all right, to form an alcohol and two methyl groups attached to this R group. All right, and of course you need to finish this off with water to be able to do that. Okay, what that means is what we get is something that looks like this. Here's our OTMS group, and then we have our alcohol and our two methyl groups. Now we can remove that protecting group using TBAF and bring back our alcohol. All right, and just like that, we have accomplished this transformation. So you see, if you only want to operate in one region, you need to protect the alcohol group, go about your reaction, and then finally replace the protecting group you put in with your alcohol group. If you kept the alcohol group without protecting it, whenever you treat it with magnesium and your ketone and your water, your alcohol will have a side reaction and transform, and we don't want that to happen. All right, fantastic. So now we've talked about preparations of alcohols and phenols. Now we want to talk about reactions. So on to all the reactions with alcohols. Now, with alcohols, you can use SN1 reactions to replace the alcohol. All right. Tertiary alcohols are going to be needed for this, right? Because you're doing SN1 reactions. All right. And so ultimately, you can replace this alcohol group back with a halogen if you wanted. We can also do SN2 reactions. Primary and secondary alcohols can react with things like SOCl2 and pyridine, or PBr3 via SN2 reactions. What these do is really awesome. If you have an alcohol group and you react it with these reagents, you replace the alcohol with a chlorine group. If you have an alcohol group and you treat it with PBr3, you can replace the alcohol with bromine. Other ways of doing this is if you have a primary alcohol, you can just treat it with HBr, and this will also convert it to bromine. Or if you have an alcohol group, secondary alcohol, you can convert it to a better leaving group. OTS will convert it to a tosylate group, and then treat it with your halogen like bromine or chlorine, and that will replace it as well. Now, as you notice, this proceeds through inversion of configuration. So do these. These will proceed with inversion of configuration. Now, for the mechanism of treating alcohol with SOCl2 to get that chlorine, here is the mechanism. You're going to be, your alcohol will attack your SOCl2. It'll attach to the alcohol. Pyridine serves to deprotonate your alcohol. All right, and then this is finally going to be a good leaving group. So when your chlorine comes into attack to replace, this group can leave. All right, and as for treating alcohol with PBr3 to replace the alcohol with a bromine, you just pretty much are using your bad leaving group alcohol to attach to this PBr3, which is now serving as a good leaving group. So when your bromine comes to attack your alpha position, this group can leave and your bromine can come in and replace it. Fantastic. Let's do some practice problems with this now. What we're going to want to do is figure out the kinds of reagents we would need to go from substrate to final product. We have an alcohol group to start off with. We're ending with a bromine. What we can do is just take advantage of PBr3, easy, and what it will do is it will replace our alcohol group with bromine by making the alcohol first a good leaving group and then having bromine to come in and attack and replace. Of course, again, we told you it operates under inversion of configuration, which is what we see here, so perfect. Now for C, all right, we're trying to convert the secondary alcohol into a secondary alkyl chloride. We can treat this with SOCl2 and pyridine, and what will occur is this alcohol group gets converted to a better leaving group. So when your chlorine minus comes into attack, you have something that can leave, and therefore you get your chlorine attached here. Again, we told you this operates with inversion of configuration. You see that here at play. So perfect. Now, with alcohols, you can also do elimination reactions to form double bonds. You can use concentrated acid for this. For tertiary alcohols like this one right here, you can treat it with concentrated acid. It's going to proceed through E1 reaction to form a double bond. We've covered this in chapter 7. Also, when more than one product is formed, recall that elimination generally favors the more substituted product as the major product. All right, so that's something that's very important to remember. Fantastic. Now, alcohols can also go through oxidation reactions. We will now see how we can convert an alcohol back into a ketone or aldehyde. So we've covered how to go from a ketone or aldehyde to an alcohol. That was called a reduction reaction. Now we're going to learn how to go from an alcohol back to a ketone or aldehyde. This is called an oxidation reaction. Okay? We can convert an alcohol to a ketone or aldehyde in multiple ways. There's 3 sets of reagents that will accomplish this. You can use chromic acid, all right, to accomplish this reaction. One note on chromic acid, okay? This is very important. It will only work on a secondary alcohol. A secondary alcohol can be converted to a ketone. If you had a primary alcohol and you treated it with this set of reagents, chromic acid reagents, what will actually happen is you're going to form a carboxylic acid. You would think you would form an aldehyde, but it's actually the aldehyde is not isolated. So when you treat a primary alcohol with chromic acid, expect to get carboxylic acid. But when you treat a secondary alcohol with chromic acid, you're gonna get your ketone, where you preserve your R groups and your alcohol gets converted to a carbonyl. Other ways to do this is using PCC. All right, this will also work. It will work with also primary alcohols to give you aldehydes. So this works with primary alcohols to give you aldehydes. It will work with secondary alcohols to give you ketones. DMSO also does the same thing. It will react with primary alcohols to give you aldehydes, and then it will react with secondary alcohols to give you ketones. This is actually has a name when you use DMSO COCl2. It's called Swern oxidation. All right, so any one of these sets of reagents can potentially work to do the oxidation reaction of alcohols to get ketones or aldehydes. And now what we're going to do is we're going to jump into a few practice problems before we do some synthesis questions to end this chapter. Excuse me. Predict the product for each of the following transformations. We have this alcohol. It's a tertiary alcohol. We're going to be treating it with concentrated sulfuric acid. That means we're going to be getting elimination. This is going to proceed through an elimination reaction. What we're going to be getting are double bonds. Okay. Now, there are 2 places that this can react. If you remember, this is going to be a friendly reminder of our chapter 7. All right, here's our alpha position, and there's 2 unique beta positions, okay? This position right here and this position. By the way, this is equivalent to this, so we only need to worry about 1. Okay, that means we can get an elimination reaction that occurs here to get a double bond, or an elimination reaction to form a double bond here. So that means we're going to be getting 2 products from A, okay? One that will look like this, and one that will look like this. All right, this is just chapter 7 review, okay? Reactions of alcohol groups through concentrated sulfuric acid is going to get us elimination products. These 2 specifically. Now, if you remember, your major product here is going to be your more substituted alkene. So this is going to be our major product. Fantastic. Let's do B now. B, we have this alcohol group, secondary alcohol group. We're reacting with TSCl. This is going to take our alcohol, all right, and make it a tosylate group. All right. So what this is going to do is going to take our alcohol and make it a tosylate group. Now it's a good leaving group. So when we react it with the second part, sodium ethoxide, we're going to get a elimination product. All right, we're going to get an elimination product that looks like this. Fantastic. And this is going to be our major product. Fantastic. Now let's continue doing more practice problems. Okay, here's A. We have a secondary alcohol. We're reacting it with chromic acid. All right, sodium chromate, sulfuric acid, and water. Okay, what is going to happen here is we're going to convert our secondary alcohol into a ketone. So wherever this alcohol group is now going to be converted to a carbonyl group. And so our product is this, and that is it. All right, now if we look at B, this is a primary alcohol. We're treating it with chromic acid. What did we say happens when we treat a primary alcohol with chromic acid? No, we're not going to get an aldehyde like you would expect. We're actually going to get a carboxylic acid. All right, and so we're going to get a carboxylic acid. Fantastic. All right, now I'm going to leave C for you to attempt. Okay, keep in mind that here's our alcohol group. We're treating it with, this is our chromic acid kind of derivative here. What are we going to get? Let me know what you think in the comments below. But now what we want to move in as a final note for this chapter is we're going to do a few synthesis problems just to put everything we've learned so far in OChem 1 together with what we just learned in this chapter. So we're going to go ahead, we're going to do A. Let's make note of what's occurring, what's changing between our starting material and end product. All right, in our starting material, we have a triple bond. There's actually 2 carbons here. But at the end, what we have here is we still preserve these 2 carbons, but now we've attached an alcohol group. Okay? Now, we don't know a direct way of adding, we don't know one direct way of going from a triple bond to a primary alcohol. What we do know is we can go from a double bond to an alcohol. So here's our starting reagents. All right, here's our end product. Okay, we don't know one direct way to go from this to this. But what we do know is if we had a double bond there, we know how to treat a double bond. Okay, if we had a double bond where that triple bond was once, all right, we can easily do hydroboration oxidation to add the alcohol group to the least substituted position and hydrogen to the more substituted position. So if only we were lucky to have a double bond here, we know how to treat a double bond to get a primary alcohol. Easy. Hydroboration oxidation. And the reagents you would need are BH3 and THF along with peroxides and sodium hydroxide. This could take our double bond into that primary alcohol, but we don't have a double bond. So is there a way to convert our triple bond to a double bond? The answer is yes. All right, we can just do a hydrogenation reaction, and specifically we can add as a catalyst here Lindlar's catalyst. Fantastic. And that means we get that double bond. We can convert the triple bond to a double bond. Now we know how to work with a double bond to add the alcohol group. We notice that the alcohol group needs to be added to the least substituted position. So that means that the kind of hydration reaction we're looking for is hydroboration oxidation, because that's the hydration reaction that will proceed through anti-mark addition. And there you go. We've developed the synthesis pathway to go from substrate to end product. Fantastic. All right, now I'm going to do one more for you. All right, and we'll leave the third one as one that you can attempt on your own time. All right, so B is the opposite, sort of, in theory, going from alcohol to triple bond. So let's do that one together, and I'll leave C for you to attempt, okay? So our goal is to take this primary alcohol, convert it to a triple bond. Now, what we can do here is work step by step, all right? We're starting with no double bonds at all, no triple bonds, just single bonds. But we have an alcohol group that we can take advantage of to convert this primary alcohol to a double bond as a first step. And one way that we can do this is through an elimination reaction using concentrated sulfuric acid and heat. What this will do is it will take that alcohol group and it'll convert it to a double bond. Now, there's another way to do this, okay? What you can do is you can convert the alcohol group to a good leaving group. All right, so I'm going to give you an alternative way to do this. You can use TSCl and pyridine to convert the alcohol group to a tosylate group, good leaving group, and then treat it with something like sodium ethoxide to do the elimination reaction. We saw an example of this up here. somewhere. So that would have taken advantage of something that we just recently covered. Or again, you can use concentrated sulfuric acid. Either one of these ways will take your primary alcohol and convert it to a double bond. I drew this incorrectly. Let me draw this better, to a double bond like this. So sorry. Right, because we have 3 carbons. This is our leaving group. We formed the double bond here. Perfect. Now, what we can do is we can try and take this to a triple bond, but we can't go directly from double bond to triple bond. What we can take advantage of is an addition reaction that we can then do an elimination reaction to again to get the triple bond. Okay, so there needs to be an intermediate step here that we can then take to a triple bond. All right, that means we need to do an addition reaction here and then another elimination reaction here. All right, what can we do to this double bond that will help us take it to a triple bond? Well, if we remember, we can form triple bonds with dihalides. So if there are 2 halogens present, what we can do is then do an elimination reaction with those 2 halogens to get that triple bond. So what we want to do to this double bond is add some halogens. We're going to halogenate this double bond, and we can use Br2. What will happen then is we're going to add bromine to both sides of the double bond. Now we have a dihalide. Dihalides are perfect for triple bond preparations. Now that we have this dihalide, what we can do is treat it with excess sodium amide and water. And water to take the dihalide into a triple bond. And this synthesis pathway will take us from our primary alcohol all the way to a triple bond. Attempt C and let me know what you get. Other than that, we've completed chapter 12. I highly recommend you do more practice problems. If you have questions, reach out to me. Other than that, good luck, happy studying, and have a beautiful day.